Chapter 7, Number 3. A farmhand pushes a 26-kilogram bale of hay 3.9 meters across the floor of the barn. If she exerts a horizontal force of 88 newtons on the hay, how much work has she done? So we begin, as always, with our picture. And we say we have our bale of hay being pushed by our person, our farmhand, and over the course of some distance, which we are given, which I'm going to call D, she exerts a force, which I'm going to call FP, and of course we have some mass M. So that's our basic thing. We are basically assuming, actually no, we're told we only know we only care about how much work she has done. So we only care about the work done by FP. So this will be actually relatively straightforward. The work done by the pushing force here is going to be, well, the force times the distance times the angle, cosine of the angle between them, which is cosine of 0 or 1. Or if we just remember, the displacement is fully aligned with the force, so the work is just the force times the distance. Do have to keep stressing that's because they are fully aligned, that D points some direction and FP points in exactly the same direction. So then we just get 88 newtons times 3.9 meters. And that's 343.2 joules, which we should round really to 2 decimal places because we have only 2 sig figs. So this really becomes 340 joules, which the textbook writes as 0.34 kilojoules because of this weird quasi ambiguity with that trailing 0, with which Walker is incredibly uncomfortable. We notice, kind of surprisingly, that the mass played no role, which is kind of interesting. It's because it might have shown up via the friction, via the normal force, via the weight, but they gave us the 88 newtons. So we don't really care how heavy the box is. We know that she is able to produce 88 newtons on it, so this is the work we'll do. It would play a role in how much kinetic energy it picks up, so it's not that it's irrelevant, but it's irrelevant to this particular problem.